This is the third update lecture for Frontiers and Controversies in Astrophysics. We're doing this little series of update lectures to bring the material up to date from when the lectures were first recorded in 2007. This particular lecture will have to do with cosmology. That's the third and final segment of the course. Cosmology is the study of the universe as a whole, the origin, evolution, and structure of the universe considered as a single object. And over the past 5 years, something quite remarkable has happened in the study of cosmology. And that remarkable thing is that nothing fundamental has changed about the way we think about the universe. Now, why is that remarkable? That's remarkable because in the previous 10 years, in the 10 years leading up to 2007, there had been a drastic change in what we think the universe consists of. And we had come up with this model of the universe in which over 95% of the constituents of the universe were things we didn't understand at all. We gave them names and labels: dark matter, dark energy, but we actually don't understand any of that. But it turned out that we had good reason to believe that over 95% of the material in the universe came in these forms, and that the ordinary material with which we're familiar, atoms, radiation, and so forth, was actually less than 5% of the stuff in the universe. Really a kind of a bizarre situation. Over the past 5 years, a vast amount of new data has come in. New models and new computer simulations of the universe have been performed, and the consequence of all of this stuff is that this very strange vision of the universe has been confirmed repeatedly over and over again by all of the information we have at our disposal. And so people are really starting to believe that this might turn out to be true. The basic information that we have is kind of summed up in this graph. I showed a version of this, I think, at the end of the lecture series. And what this is it plots the amount of dark energy in the universe versus the amount of dark matter in the universe. And each one of these different colors is a different way of constraining the dark matter and the dark energy. So in the course, we spent most of our time worrying about supernovae. The supernovae it turns out, demonstrate that the universe is expanding faster and faster and faster. So there must be some universal repulsive force in the universe that's pushing it apart at an ever-increasing rate. This is what we call dark energy, and the discovery that the supernova evidence showed that the universe was expanding faster as time went on rather than slower. That was what was discovered in 1998, and that began this change in our view of what the universe consisted of. And for this to be true, there has to be more dark energy in the universe than there is dark matter. And so that's this region of the plot. And you can figure out how much more as well. If the dark matter, there's 0.4 in whatever units these are, then the amount of dark energy has to be something like 0.8. And so you have a diagonal in this direction here. The orange stuff here is from observations of the cosmic microwave background, and in particular of the fluctuations, the non-uniformity of the cosmic microwave background. And I'll come back and talk about that a little more later on. And what you can derive from those is the total amount of dark matter and dark energy in the universe. So this number has to add up, plus this number has to add up to something that's more or less the same. And so if there's less dark matter, there has to be more dark energy. That's why this one goes in this direction. And then the green has to do with the clustering in the universe, how the fact that galaxies are not uniformly spread across the universe, but they're clustered into clusters of galaxies and even bigger structures, whereas there are other parts of the universe that are voids. And how much clustering there is, which is something we can measure, has to do basically with how much dark matter there is. It doesn't depend so much on how much. It depends a little on dark energy, but not so much. And that's why that's kind of vertical, because it picks out a particular value of the dark matter. And so the remarkable thing turns out to be that there are these three ways of measuring how much dark matter and energy there is, each one of which defines a line in this graph. Now, if you have two lines in a two-dimensional graph, they'll cross somewhere, unless they're perfectly parallel. They'll cross somewhere, and that's not a big surprise. But if there's a third line, it doesn't have to cross where the other two do. In fact, in general, it won't. So you could have two lines that cross here. The third line could be over here somewhere, and it would cross each of those other lines somewhere, but not necessarily at the same point. So the fact that we have these three fundamentally different ways of measuring things, and they all agree, is basically the basis for why we believe this is true. And what has happened, this particular plot is from 2010 with some of the latest observations included. Each one of these methods is being worked on all the time. And the range that is allowed is getting narrower and narrower and narrower. And as that is being done, they still cross each other. And so it is now the case that the only region of this plot that is allowed by all three of these methods is this little region in here. And that gives us the parameters of what has come to be called the concordance cosmology, a cosmology which includes all evidence that we have to date. Let me make one passing remark about this plot. In the previous plot, this stripe here was labeled clusters of galaxies. Nowadays, we have a new fancier name for it. This is one of the things that happened in the past 5 years. We call it baryon acoustic oscillations. That means the clustering of galaxies. Baryons are ordinary matter. That's what galaxy consists on. Acoustic oscillations are why they cluster. And I'll come back to that in a little bit. Later, but I just wanted to point out that there's this excellent new jargon term which we use for that part of the plot. So here is the concordance cosmology. It's also called lambda CDM. Lambda is the symbol we give for the dark energy. CDM stands for cold dark matter, and so this is a universe which is dominated by dark energy and dark matter. And the amount of dark energy, that's the lambda here, is 0.73 out of the total. The amount of dark matter is 0.23, and that leaves for ordinary material, the B is for baryons there, for ordinary material, 4%. And this is these are what we believe to be the constituents of the universe. There's also a couple other things we know. The Hubble constant is how fast the universe is expanding right now. This is given in units of kilometers per second per megaparsec. What that means is if you look at something a megaparsec away, it's moving away from us at 72 kilometers per second. If you look at something 10 megaparsecs away, it's receding from us at 720 kilometers a second. And so this is expressed in kilometers per second per megaparsec. For 2 generations, people argued about whether this number was 50 or 100. And so, of course, the answer is 75, more or less. If you put all of this stuff together, you can calculate with considerable precision what the age of the universe must be, how long it has been since the Big Bang occurred. And the answer to that is 13.7 billion years. The G stands for giga, which means billion. So astronomers like to talk about giga years. And so the universe, if you believe these numbers here, is 13.7 giga years old. And it's really quite remarkable. We have that to several decimal places now. And that's the really extraordinary thing about the concordance cosmology, is that these numbers have been around. People have been exploring them now for in a large number of ways for some number of years, and it keeps coming out to the same answer. So much so, as I said, people have started to believe it. And you can tell that people have started to believe it because they gave a Nobel Prize for it. And the 2011 Nobel Prize in Physics was awarded to people who made this discovery about the supernovae and thus essentially discovered the existence of dark energy. And so Saul Perlmutter and Brian Schmidt and Adam Rees were given the Nobel Prize. These were the leaders of the two teams competing with each other who made the same discovery at the same time. There was some issue about who should be awarded the prize for this. It was clear that the discovery was prizeworthy. Perlmutter was the clear leader of one of these groups, but the other group didn't have a clear leadership a clear leadership structure in quite the same way. There was a lot of independent actors working together. Schmidt and Rees were the principal authors of the key papers and indeed did much of the work and leadership, but they were both graduate students and postdocs of a particular guy at Harvard named Bob Kirshner who didn't get the award, and there were 40 other people who might have who have contributed very strongly to that. And this, I think, points up a problem that we're having in science these days. It's getting harder and harder to associate a particular scientific advance with a particular person. And the whole concept of the Nobel Prize, among other prizes, but the Nobel, of course, is the most famous, is that people, individual people, make discoveries. And back when there was Einstein and Planck and Bohr and all these fabulous people a century ago, that was kind of true. Now people work in these big teams because the projects are too big for any one person. And so the whole concept of giving prizes to people has become a little problematic. The Nobel Prize in particular has a rule. You can only give it to 3 people at once. And so they picked Saul, who was the head of one of the groups, and that was fine. And you could have picked a whole bunch of people on this side. And indeed, there was another prize that was given for this, the Catholic Prize, where they gave it to the whole group. So everybody got 1/65th of a prize or something like that. And so there's a problem, I think, these days in assigning credit. Be that as it may, this discovery clearly worthy of a Nobel Prize. It revolutionized our understanding of the universe. And of course, they don't like to give prizes to things before people really believe that it's true. And so the fact that they finally got around to giving the Nobel Prize for the discovery of dark energy means that the physics community has decided that dark energy really exists. So where do we go from here? Now that we have the basic parameters of the universe, what do you do next? And one of the things that's being done is the study of cosmic structures, structures in the galaxy, in the universe, and how they evolve, where they came from, and how they're likely to evolve in the future. So if you look as far back as you can in time, back, as you look to something further and further away, you're looking back in time because the speed of light, you have to account for the length of time the light has been traveling towards you. The furthest back you can look is the cosmic microwave background. That's emanating from material shortly after the Big Bang, and the waves of light that have been emitted from that have been redshifted, have increased their wavelength by a factor of 1,000 between when they were emitted and now. One way to think about that is that's the amount the universe has expanded since that light was emitted. So this light was emitted when the universe was 1,000 times smaller than it is today. This is a famous picture from the COBE satellite from the 1990s when they discovered that it's not quite uniform. It's very close to uniform across the sky. And this is color-coded for high-density and low-density regions. And the variations between the high-density and the low-density region are about a part in 100,000. So not big variations, but this was a very sensitive instrument that could see it. If you look in the nearby present-day universe, you can also see structure. This is the distribution of galaxies in a particular survey, the 2-degree field survey done by people in Australia. And you can see there is some region where there are lots and lots of galaxies. There are some regions where there are very few galaxies, voids we call them. And these are structures as well. In this case, you're looking at galaxies with a redshift of between 0 and 1. Basically, the way to interpret this map is we sit here and we're looking in one direction there and one direction that way. You can't see up and down because our own galaxy gets in the way. But the amplitude of the variations is very much bigger. If you compare the density of the material in this room as compared to the density of material in the intergalactic void, there's 10 to the 29 times greater density of material here. And in fact, it can be a difference of effectively infinity if you look at black holes. But there's, instead of 1 part in 10 to the 5, we now have 29 orders of magnitude difference in density, and so the clumping is much more now than it was back then. Nevertheless, the hypothesis is that these tiny ripples in the cosmic microwave background have been amplified over the history of the universe to create these enormous differences in density that we see today, and that they're basically the same thing. It's just that over time, they get bigger and bigger, because if you have an overdense region, it has extra gravity, it pulls stuff in. And the underdense region doesn't have as much gravity, and the stuff streams away. So over time, small density perturbations will be amplified. But there's an interesting problem in that there's a region in time between the cosmic microwave background and the galaxies we see today, which you don't see any radiation from. This is what's referred to sometimes as the dark ages. So at a redshift of 1,000, you can see the cosmic microwave background. That's the moment where the universe goes from being opaque to being transparent. The reason it does that is it's become cool enough for hydrogen, for electrons and protons to combine to make atomic hydrogen. Atomic hydrogen is much more transparent than ionized hydrogen. And so when it's hot, you can't see through it. When it cools down and the hydrogen atomic hydrogen can be created, all of a sudden the universe is transparent, and you see this sort of hot, opaque wall on the other side. But then it's transparent. Nothing happens. No radiation is emitted until much, much later, when the density contrast has become sufficiently great that stars and galaxies actually begin to form. And between the cosmic microwave background and the first stars and galaxies, there's this long period of time where you have no information because no photons were emitted. And so if you want to test the hypothesis that the stars and galaxies evolve from these tiny little fluctuations that you observe in the cosmic microwave background, there's a problem from an observational point of view, because you can't see this process going on until stars actually begin to form and begin to shine. So the approach has been to model this with computer simulations. So what you do is you start out with the observed structure of the cosmic microwave background, the size and the shape of those tiny irregularities. And then then you do a computer model which includes two different effects. One is the fact that the universe is expanding. And now that we have the concordance cosmology, lambda CDM, we know how fast it's expanding, and how much dark energy is pushing it out, how much dark matter is pulling it in. And then you also add to that the law of gravity, Newton's law of gravity, which, as I mentioned before, has this effect that the dense regions pull stuff in, and the low density regions lose their material to the high density regions. And with those two effects, you simply calculate the clumping of the matter and how much the matter clumps as the universe expands. And you keep this going from when the cosmic microwave background happened to the present day. And you say, all right, if I run this little computer program and I end up with a certain amount of clumping, I can then compare those clumps to the clumping of the galaxies that we see today and see whether it works, whether the clumps are the right size and shape and density contrast. And it turns out that this works really well for lambda-cold dark matter universes, but not for other possible values of the cosmic parameters. This is the baryon acoustic oscillation calculation that I was discussing before, and that's what gives you the green stripe. That's the range of cosmic parameters that makes the clumping work out. So let me just show you an example of one of these computer simulations. These are kind of cool to watch. Let's see here. So this is a bunch of material, and it starts out in a fairly uniform state. And as time goes on, you can see it clumps more and more and more into these structures. You can see these long structures surrounding voids where there's no material at all. There's kind of one in the center of the box. I'll show it again. And what's being kept track of in the upper left-hand corner here, this quantity z, that's the redshift. This particular simulation only goes from a redshift of 15 to the current day, but the principle is the same. And so I'll show it to you again, and as you'll see, it starts out very uniform and it clumps more and more. What this isn't showing is that it should get bigger. The universe is expanding. So really it should start 13 times smaller than it ends. But then you can't see what's going on. And so what they do is they're changing the scale as it goes along to keep the box the same size. So you have to imagine in your head that this box is increasing in size along with the redshift. So let's look at it again. And here's the uniform start at a redshift of about 10. And as it comes closer and closer to the present time is redshift 0, you can see that the clumping gets more and more and more significant. And this is a particular range of initial perturbations and a particular cosmology. And people are amusing themselves by doing this kind of calculation over and over again on the current day supercomputers. So the idea is you start, as I said, you start with the observed structures, you apply the expansion of the universe and the law of gravity, and you see how things clump, and you compare that to what you observe. There's a little bit of a problem in interpreting these computer simulations. You have to be careful. What is plotted in that computer simulation is cold dark matter, which is the material, most of the matter in the universe. And the reason you plot that is because dark matter interacts only by gravity. But of course, we don't see dark matter. By definition, you don't see dark matter. It's dark. And so what do you see? You see glowing gas. That's what we observe. Stars, nebulae, things of this nature, those are all baryons. That's this little extra stuff that rides along with the cold dark matter. At least it rides along for a while, because gas doesn't only interact through gravity. There's also radiation, pushes the gas around, pressure of various kinds. Streams of gas can run into each other and have shock waves. And after a while, the gas is not necessarily in the same place as the dark matter is. And so the difference between where the gas is and where the dark matter is referred to as the bias in the observations. And the distribution of the gas is actually much harder to model by computer simulations because you have to include these other effects than is the distribution of the dark matter. And so this is sometimes referred to as gastrophysics. Trying to figure out where the gas is actually much harder than trying to figure out where the dark matter is, even though gas is something we understand and dark matter is something we don't know what it is. But the only thing we know about it is it doesn't interact. So one of the big research efforts going on now is to include calculations of the bias in these computer simulations so that you can actually compare the computer simulations to the galaxies and the distribution of galaxies that we see. There's also new observations being planned. The idea is to look at the radiating matter further and further away at higher and higher redshifts. We can now observe galaxies and quasars and other things out to redshifts of 7 and 8. This is much further away than we've been able to do before. And as you could see in that simulation, you expect the clustering to change over that time. So now we don't just look at how things are clustered now, we look at how it changes with time. But you need better observations to do this. These objects are very distant. They're therefore faint. You need the biggest, most powerful telescopes to observe them. They're also redshifted, and therefore their radiation is not in optical light where stars emit radiation, but in the infrared instead. And infrared observations get to be difficult from the ground. That's because the Earth glows in the infrared. That's how night vision goggles work. You can see human beings glow in the dark. Telescopes glow in the dark. Buildings glow in the dark. Astronomers glow in the dark. And so making good infrared observations from the ground is actually tricky to do. And so they are planning new space telescopes in order to carry out these observations of distant, faint, redshifted objects. So the most prominent of these telescopes being planned is something called the James Webb Space Telescope. James Webb was the administrator of NASA in the early 60s when we went to the moon. And you'll notice that the new space telescopes are named not after scientists like the Hubble Space Telescope was, but after NASA administrators, whatever it takes to get the thing built. So the JWST is a large space telescope. It's much bigger than the Hubble Space Telescope, more powerful than the Hubble Space Telescope, and optimized for infrared observations so that it can observe the most distant galaxies and stars right after galaxies and stars began to form. And they're going to stick it not in near-Earth orbit. As I say, Earth glows in the infrared, but a fair distance away at what's called the L2 point, which is a gravitational equilibrium point in a kind of triangle with the Earth and the sun and the moon. And it has this, here's the segments of the telescope itself. It takes the light from distant stars and focuses it on something out here. And this is a big heat shield. And it points toward the sun because you don't want the heat from the sun interfering with it. And so it kind of always keeps its backside toward the sun. And this is going to be the next great space telescope, more powerful, in particular for these cosmological observations, much more powerful than the Hubble Space Telescope has been. There's one big mistake in this image. This, again, is a piece of NASA propaganda. 2013, that might have been true in 2007, but I think 2018 might be more accurate now. There have been a lot of cost overruns and delays with this mission, which have turned out to be a problem. Given the economic problems we've been having for the past 5 years, the fact that this is a multi-billion-dollar project that keeps being more costly and more delayed, and the consequence is that we haven't started any new projects. And so it's actually getting to be a kind of an issue as the current generation of space telescopes get older. This is the only replacement that's really on track to be launched anytime this decade. But that doesn't stop people from thinking up new clever things to do. Here's another planned infrared space telescope called the Wide Field Infrared Space Telescope, or WFIRST. The key to this, and the reason it's different from the JWST, is the wide field. JWST will only look at a small, tiny piece of the sky at once. It'll look really powerfully and distantly at this. This is not as big a telescope as the JWST, but it looks at much more of the sky at once. And so this thing will do two projects. It will not only do the cosmology project and thus be a successor to JWST and the ground-based, and HST and the ground-based infrared telescopes. It will also be a successor to the Kepler mission that is exploring exoplanets because it has a wide field of view. And the other thing is you'll be able to see more light from the planets in the infrared than you could in optical light. And so this is planned to be both an exoplanet mission and a cosmology mission. It was ranked the #1 project by a group of scientists. Every 10 years, the astronomers get together to try and prioritize all their projects so they can present a united front to Congress when they want many billions of dollars. And this exercise took place in 2010, happens, as I say, every decade, and this was the #1 ranked space mission that came out of that project, but it still doesn't have a launch date because we're not far enough along in JWST to really commit ourselves to the next project. There's another approach that's possible in which you don't even try and look at stars. It turns out you can look at cold hydrogen gas because hydrogen gas emits radio waves at a wavelength of 21 centimeters. And even before stars and galaxies formed, you should still be able to see this hydrogen gas. And the further away it is, the more redshifted it becomes. And so you can, in principle, go back to redshifts of 20 or more, looking at just the hydrogen gas. To do this requires arrays of radio telescopes. And they have to be sensitive to very long wavelengths because it's 21 centimeter radiation, but redshifted by a factor of 20. So that's now out at 400 centimeters, 4 meter wavelengths, 4 meter wavelengths and so forth. That is to say, very low frequencies. And there are a couple of ground-based radio telescope arrays being planned. LOFAR is the low frequency array. WMA is an array in Australia, and eventually something called SKA. This stands for the square kilometer array. A square kilometer is solidly covered by radio telescopes that's going to be built partly in South Africa and partly in Australia. You need to build these things in the desert because cell phones, very bad for radio astronomy. And so the middle of the uninhabited Australian desert turns out to be the only place in the world you can really do this. So the current state of cosmology is basically the following. One of the great triumphs of 21st century science, really realized in the first decade of the 21st century, has been that we really now do understand the dynamics of the universe. What its age is, what its constituents are, how fast it's expanding, how it will expand in the future, and so forth. This is really a remarkable triumph. You wouldn't have thought that cosmology would be a science at all. It's only one object, and we're in the middle of it. How can you figure stuff out? But we can, and so we have this concordance cosmology, which really seems to be true. But we don't understand the details of the things the universe contains. We don't know what the dark matter is. We don't know what the dark energy is. We haven't mapped the clumping of the gas during the dark ages, and we don't understand the gastrophysics of the radiating objects, the stars and galaxies themselves. So there's plenty of work to be done in the 21st century, but it will all be based on this basic picture of cosmology that's been developed since 1998.